Welcome back, everyone. Our next speaker is Azat Gainutdinov from Tool. He will tell us about non-semisimple link and free manifold invariants, algebraically, algebraic and strong.
Thank you. First of all, I would like to thank organizers for invitation and for organizing a great workshop, and especially special thanks to Ram for yesterday's whiskey tasting. It was really great. However, today I don't think so great as compared to yesterday. I hope it will not spoil my talk. But let's see. Right, so this will be I will talk about the interplay between topology and algebra, and it will be about results of a recent paper with Untitled from Hamburg and our previous student Hans Berger. Let me start with context. We are interested in topological quantum field theories, and for the very good definition of topological quantum field theory that goes like that. Yeah, it's a symmetric monoidal quantum from a category of n plus 1 cobordism to the category of finite-dimensional k-vector spaces. This will be my definition. Loosely speaking, TQT it's a study of linear representations of cobordisms. So to close the manifold, we associate a vector space that is called state space. To cobordism between n manifolds, we associate a linear map between corresponding vector spaces. And group of cobordisms positions linear maps and joint union, or which corresponds to the product structure and cobordism category. It's just another product of vector spaces. And for this talk, I will be interested in N=2. So we talk about 3, 2 TQT, and the motivation comes from static representations of mapping class groups, plus surfaces, and also mapping free manifolds, because if you have a TQT, in particular, gives you a state for every handle body, and then using mapping class group on the surfaces, we can glue such handle bodies to construct an invariant of free manifold. Idea, I mean, the approach we follow goes back to Riot. We use algebraic tools. So to generate such TQTs, we have an input data. It's a modular tensor category. And let me first, and it will be not necessarily semi-simple. So it's rather general notion. I will introduce it. But every modular tensor category is first of all a ribbon category. And a ribbon category is a gadget that allows you to construct invariants of framed links. Why do we need that? Because we are going to use the surgery representations of manifolds. And in surgery representations, we get a framed link. Okay, so first of all, we need to define invariant framed links. And this is a ribbon category allows you to do that. So first of all, we have a tensor product, it's monoidal category. Plus, of course, there's some associators, it's pentagon conditions, and so on. There's tensor union. For most of my talk, it will be I will assume that tensor union is simple. Actually, I will need to assume that it's simple. And duality morphisms. So I will need evaluation. So for every object should have left and right dual, and I will need duality maps, evaluation in both directions, and co-evaluation maps. And because we're going to talk about nodes and links, we need to deal with and we will talk about diagrams of nodes and links. So we'll see breakings, and this ribbon category. It tells you what to do. First of all, x under y is isomorphic to y under x. This is called braiding isomorphisms. But to be a braiding, it's 5 factor they call hexagon conditions. And which guarantee that you get a representation to braiding on home spaces. And finally, what the ribbon structure is about called twist isomorphisms. They are certain element in the modus of identity functor. So for each x, we have isomorphism from x to itself, and it's quite different conditions. And conditions were designed so that they're safe to produce frame-link invariants. And we need graphical presentations of these morphisms because they all come from topology. So I will label I will have a graphs, general ribbon graphs, and I will label components by objects. So this is and they will be directed. So the direction up means I have identity on x, and direction down means star on blue. And then I have evaluation, correlation maps, with caps and tabs. Braiding is just by the symbol of braid, and a ribbon twist, which will be responsible for the framing. They are just these little ribbons. Okay, and in graphical picture, we have composition just vertical stacking of such graphs, and tensor product of morphisms is just horizontal juxtaposition, and the same axioms, they guarantee invariants on the isotropy and frame random Meister moves. Also, I will use this relative correlation maps to define a trace, because in the end we want to calculate numerical invariance, and typically to a frame link to construct, for example, you take its braid presentation, and then you evaluate in the category, and then you get some more. And then to get an invariant, we need to take a trace of such a morphism. And this is called categorical trace. So you frame in the morphism of your object in the category. You can pre-compose with correlation and evaluation map. And it gives you the morphism of your tensor union. And because I'm working with algebraically closed field, it's just a number. And tensor union is simple. Okay? So that's a trace. So that was a ribbon category. Now modularity of modular tensor category, it's a certain condition. So now it's not a structure, it's a property of ribbon category. And it's a property of non-degeneracy of the braid. What does it mean? Let me introduce the transparent objects. So I say object in my category is transparent. If double braiding of this object with every other object in my category is nothing, it's just identity. So it means that's why it's transparent. You can just pull it through the string. And we go category is factorizable, braid category is factorizable, or we say braid is non-degenerate if the only transparent object that has the units and the data size. Okay. And this is the definition of model tensor category we use. It's a factorizable tensor category, or with non-degenerate braiding, plus ribbon structure, plus it should be finite. And finite condition is, it means that basically we are working with representations of something, of some algebra. So as a k-linear category, it's just equivalent to a finite dimensional representation of a finite dimensional Scientifique algebra. Okay, so particularly it's a billion, it has enough projectives, it has finite many isoclasses of simple objects, it doesn't have to be semi-simple. And also we require tensor unit to be simple and self-moving. Okay, so that's a finite condition. But otherwise, as I said, it might be non-semi-simple, it might contain continuously many decomposable objects and so on and so on. It's just we just require finitely many class of simples, finite comp spaces, and so on. And then if the addition category is semi-simple, this I will call modular fusion category. And then it's a modular in the sense of derive. So derive introduced notion of modular fusion. I mean, at that time they were called modular tensor category, but if it's semi-simple, I don't emphasize it, the fusion category. Essentially, using your ribbon data, you calculate the variant of your Fox-link, colored by your simple object, say xi, xj, you get a matrix of rank of dimension of number of either classes of simples. If this matrix is invertible, you call the category modular fusion category. And this condition is equivalent to triviality of transparent objects. Let me give you an example. So first, non-semi-simple modular tensor categories. That's my favorite for the example of non-semi-simple modular tensor categories. It's based on very simple piece of very simple data. You just take an even dimensional vector space, say complex vector space, and a symplectic form of such vector space, and it generates your modular tensor category. How? Okay, this is my V is my even dimensional vector space, and I is my basis, vector spaces. I consider Z braided algebra, just exterior algebra of this vector space. And you should think about it as a commutative and co-commutative co-algebra in a sphere. So in particular, co-product of all FIs is just like Fourier algebras, FI tensor 1 plus 1 tensor FI. So it's Z braided co-algebra. The the standard braiding structure on category of modules for such a external algebra is symmetric structure, is a symmetric braiding. Is the braiding coming from a spec, because this algebra lives in a spec, I mean, and co-commutative, this category of modules inherits braiding from the spec. But this is not interesting braiding. So actually what you can do better, you can introduce almost undegenerate braiding. For this, you can define what we call universal arithmetics. So it's just exponent of my basis coupled to my fixed symplectic form. Okay. So this is the well-defined element in a tensor square minus stereo, right? Because this is I the square for 0, and so it's a well-defined element in the square of my stereo algebra, and this element defines the braiding on the category of modules of this stereo algebra. So how it defines? I mean, like algebra can act as a product of modules. How do you swap them? You first act by this R matrix. And then you use swapping in a spec. So it will be with a sign. And ribbon structure now is given by action of so-called ribbon element. So on every object, on every representation, you act by this exponent where you sum over I less than j to omega ij by j. Okay, so, right?
So your exponential with x to the n, you take n-fold exterior power then?
Yeah, formally you expand the exponent, right? So you just take like exponent of this, you got 1 plus this, right? The sum plus 1 over 2 factorial square the sum and so on. Right?
That's when you use the wedge there.
Yeah. I mean, like in my case, right. I mean, I wrote tensor product, but it's a wedge. No, okay. Here tensor product is in a spec. But because squares of all my generators go to 0, so the exponent is fine. Okay, about transparent objects. So with this braiding, there is not only tensor unit, there is another. So the algebra has only 2 simple objects. So the category is quite non-semisimple. Maximal length of projected cover grows as 2 to the 2n. But the category has only 2 simple objects. It's even, I mean, respect to grading, even dimensional. So it's ground field of degree 0 and or of degree 1. So there are 2 simple objects, they both dimension 1, and actually they form a set of transparent objects. So it's the category as spec. And I will need to so it's not model tensor category, but you can solve this problem by passing to so-called Z graded extension. So this is what I will call category symplectic fermions. It's my original category, but I can extend by some semi-simple category. It will be now degree 1, but in the sense of monoid or tensor product. So it has only 2 simple objects. And the corresponding algebra, you can realize this category. I mean, I'm not explaining to you how I introduce tensor product structure of grading. It's possible. Actually, the specification of such extensions, that graded extensions, by Gilaki and students, there are only 16, up to equivalent, there are only 16 possible extensions, such a category, to non-degenerate. And I'm thinking about a particular one. And so this symplectic fermion category, it's model tensor category. I'm not giving you the full structure. But as an algebra, you should think about it as here we have a stellar algebra or Grassmann algebra with 2 generators, and then you have a Clifford algebra with 2 generators. The representation category of these guys is simple, and you have smash product with Z2, which corresponds to this fermionic parity. Okay, so it can be realized by not by a full algebra structure, but a quadratic algebra. Okay. So this is an example. So another example coming from quantum groups. Let G be a simple finite-dimensional algebra, and Lustics in the 90s introduced so-called small quantum groups. They are defined, they are finite-dimensional group algebras, and they are defined as a kernel of, they define as Frobenius kernel of Lustig specialization of quantum groups at roots of unity to universal relative algebra of G. It's finite dimensional, and actually, if order of root of unity is odd, at least for APE type, the tensor category of finite dimensional representations of such a Hopf algebra is more tensor category. There are more exotic examples of model tensor categories coming from the special theory of vector separator algebras. We'll probably hear about it today. For example, triplet W algebras, symplectic fermions, vertex separator algebras, and it's not a coincidence of the names. So the first example, I presented it in a very simple form in Hopf algebra terms, but actually that category is very much fundamental because it's Riemann equivalent. At least in some cases it was proven, in some cases it's conjecture, to representation Riemann categories of representations of this very fundamental class of vector separator algebras. And there are many others to find theories. So we have plenty of model tensor categories. So this was non-semisimple cases. And when I will talk about topology, I will relate it to semi-simple cases. So one of the sources of modular fusion categories are coming from semi-simplifications. When we quotient my category by negligible morphisms, recall I was taught yesterday, he was talking about this. And then we have a projection in factor from your original non-semi-simple category into semi-simplification. Typically, this semi-simplified category contains many might contain uncountably many objects. They're all simple. This happens in the case of this symplectic fermion category with n bigger or equal to 2. And but what I'm going to take the image generated by simple objects of my category. It's not, I mean, I don't know if you always get a finite category, but in many examples, I know this way you get a fusion category. And the example is that if C is reflected Fermion category, in this case, you get just a vector. Semi-simplification in this sense gives you a vector. And if it's small quantum SN2, you get this Berlin modular fusion category mentioned by Pavel yesterday. And there are also more exotic examples of semi-simple model tensor categories related to BOA representation theory, performance nets, and so on. Okay, let me now talk about QT. So the ideas we're going to use, it goes back to Recherche and Riot construction of the QTs. So at that time, if you give me a modular fusion category, Riot can, so semi-simple, for example, coming from simplification of something like quantum groups. So the Riot construction gives you 3 manifold invariants, closed and oriented, but more generally it gives you 2 plus 1 TQT. Recherche and Riot, they first provide construction of 3 manifold invariants, and then Riot in his book, for every model fusion category, he explains how to construct 2 plus 1 TQT. So where objects are surfaces in cobordism category and one morphisms are cobordisms. So this TPFT produces projection representations of mapping class groups. I will call them node enriched and right type. And the particular property is that representation of dead twists always of finite order. So this is a specific property of such representations. It's basically related to the fact that category is semi-simple and finite. Riemann axioms, they force your Riemann twist as a part of data of my category to be, first of all, diagonalizable and in finite order. And this Riemann twist in my category is responsible for the action of den twist on the topological side. That's why mapping class group representations, they are of this type, only finite order representations of den twists. And what about 3 manifold invariants? So the idea is that you construct invariants of 3 manifolds by surgery. So we know that every closed 3 manifold oriented can be written as surgery along frame link in S3. And so if you provide an invariant of such a link, frame link, such that it respects curvy moves, right? Curve 1 move and curve 2 move. If you provide such invariant, then this invariant of a link is invariant of invariant. That's the idea. And let me give an example for length spaces. So this is surgery link for length space Q. So my surgery links, they will be this they will be this ribbon graphs, and they will be always red. And so we take continuous fractal expression at P over Q. We get these numbers AN, and this AN they play a role of framing. So it's just this chain link, and you have these numbers, it's framing, and then you do surgery along this link, and you get a length space. Okay, so how to construct such an invariant? Recherche, they proposed this curvy color. It's a formal object in category, and such that they adopted the invariant of the frame link with all components of the link colored by this object. They respect curvy two link. And this curvy color, it has very simple form. It's just sum over all simple objects in your semi-simple category, but weighted with categorical dimension of your object. Okay, categorical dimension is trace of identity. Okay, and then the theorem writes that when you color your frame link, first representation by this K, all components by the same K, you get an invariant many. So the property that, for example, because of depth lists on a finite order, it does not distinguish infinitely many length spaces among even LP1. So it's because LP1 and LP plus n, when n is order of your density of Riemann element, they will have same invariant. So it's relatively, I mean, they're interesting invariant, but they're relatively weak. So okay, and then people ask questions in the 90s. Can we avoid these quotient operations like killing digital morphisms? Can we work with the full non-semi-simple model tensor categories? If so, maybe we get new invariants, maybe they're better. And this was addressed, I think, for the first time. There was some people involved in this, because Azat Gainutdinov in 94, and more categorical approach was Recherche in 94. Basically, Recherche proposed the first definition of what should be model tensor category in non-semi-simple setting. So because it is non-semi-simple, we don't have K as a common object, because we might have continuously many objects. It doesn't make sense to sum of objects dimension. But K can be defined by a canonical point. It's an object in my category, and the topological meaning of such a point is that it's universal to every bottom tangle. What does it mean? Okay, first of all, let me give you a formal definition of this point. It's a point of this functor. So you take a pair of objects and you tensor them, and then we are looking at an object which is universal to all the natural transformations into any object in category C. So the natural transformation is very similar to natural transformations. It has now two labels, and when you insert a morphism on the second level, it just passes to the other side by taking dual, right? And so point is sort of a universal object with respect to all the natural transformations. So I will denote it just by this standard integral notation, and it's equipped with the canonical family of the natural morphisms. So it makes it a universal object. But for me, what's important, I don't want to go into details of this. What's important for this topological construction is that you can sort of be universal to every tangle. What do you mean by that? Because when we are going to okay, let's take an n-bottom tangle. So while talking about tangles, imagine you have a surgery link, like for length space chain link, and then we are going to cut every component of the link. We are going to cut. And then we're going to pull all strands of each link component down, and this way you get bottom tangle. So this part is quite entangled, but what you will have these inputs outputs, and you can think about this now tangle because using ribbon structure in my category, you will have here a kind of diagram of a tangle, right? And you you think about it in terms of string diagram in the category. So you have right. And you think about it as every component colored by object in my category and so on. It gives me a dimensional transformation, but sort of in n variables. And by universality of the coend to every such a bottom tangle, I get a unique morphism from nth power of the coend to the 10th degree. Okay, and now you can take any tuple of invariants of my coend. So they are morphisms from 10th degree to the coend. And we precompose this map, we precompose with 10th power of them. What I get a number. And this number is a numerical identity invariant of a frame link, whose closure, which is closure of B. Okay, so it gives you a way to, a formal way, the point gives you a formal way to calculate invariance of frame links, but just isotopy invariance. Now we need what Ivashenko basically proposed to calculate invariance with respect to Kirby moves. You need to choose a special alpha i's, and the special alpha i's is the integral of L. What does it mean? Actually, L it's not just a universal object in the category. It has a pop algebra structure. So it's actually a pop algebra in the category. I don't want to go into details of that, but it's very canonically defined pop algebra structure using universality of the point, using the structural morphism of your category. So it has a product, multiplication, product, antipode, and so on. Okay, these are you can define them in terms of pictures. But what we like about pop algebras, it's again, this is pop algebra leading to this braided category. And fundamental theorem for pop algebra also works here. So we have a unique morphism, which is called integral. And it's such that when you multiply, you can think about this as a morphism to L. Loosely speaking, it's an element in this point. When you multiply with every other element in the point, on the left or the right, you get lambda composed with a co-unit of the point. Okay, so it's special morphism. And it's unique up to scalar. And let me give you an example. If category is semi-simple, the coend is just direct sum of x star times of x. And the integral of this, I mean, there's pop algebra structure on such direct sum, and the integral is just sum over dimensions of x coevaluation x. That's it. It's a morphism, special morphism from 1 to L, and right. Okay, and this corresponds to the Kirby color K. So this is the theorem of Lubashenko. So the integral of the point plays the role of Kirby color. So the Lubashenko invariant of the manifold is given by this formula. What does it mean? Okay, there is a prefactor. I'm not going to explain this. L is the number of components of my surgery link. Sigma is signature of the linking matrix. And then these are from scalars. They're responsible for Kirby 1. So they guarantee that the scalar will respect Kirby 1 moves. And the integral respects Kirby 2 moves. So what is this FCL twiddle? FCL twiddle I defined you previously, right? So it's a Zist map. So we take link, we cut components, and it gives me a length tensor 1. And instead of composing with random invariants of the coin, I precompose such a map, which I get from surgery or bottom tangle representation. I compose with the integral of the coin. And the point is that it's well-defined invariant, and it's invariant of a three-manifold. And basically the idea is that this equation on the integral, defining equation of the integral, it's an algebraic version of invariance under Kirby 2 move. Okay, so what are properties? Even in that at that time, Lubashenko not just introduced this three-manifold invariance. He also formally defined projection representation of multiple groups of surfaces, a generalized right function. And then, but there was not TQT construction. And the natural question: does this construction carry more topological information comparing to semi-simplification, and can be extended to TQFTs? And in some sense, yes. In some sense, yes. It contains actually non-trivial topological information compared to semi-simplified version. So let me give you an example of this symplectic fermion. So I consider now this exterior algebra example. Semi-simplification gives you a spec, which provides you just trivial invariants. And in this paper, part of the results, we computed such invariants for all n spaces, so Lobachevsky invariants for all n spaces of PQ. But not using semi-simplification, using the full non-semi-simple category, symplectic fermions, it gives, okay, the invariants are quite simple, but they are non-trivial. It's p to the n. So the invariant is just nth power of the order of first homology group of the land space. And this is in contrast to Recherche invariant in general, because at least it does distinguish all land spaces among LP1. And also, we have a conjecture that Lobachevsky three-manifold invariant for all closed three manifolds, in this case of symplectic fermions, it's just this. It's nth power of the rank of the first homology group of the three manifold, if it's finite. Otherwise, it's zero. It's infinite. So why it's zero? It's actually related to observation also in some examples by Tsuki and Karlan that if C is not semi-simple, and if closed three manifolds, its first Betti number is positive, then Lobachevsky invariant is zero. This is related to basically to Maschke theorem for coalgebras, because if you have a free part in the homology group, you're basically evaluating integral of your coalgebra on the unit element, which is the non-zero equivalent lead category semi-simple, right? So this is a particular property, but this is property is also abstractions for defining TQFTs, because you can't construct a TQFT that would extend this Lobachevsky invariant. Why? Because again, if you have a TQFT, then what will be TQFT space, dimensional TQFT space for a surface? It should be invariant of surface times S1, right? Because we take a cylinder and we trace it, so it's surface times S1. But because its Betti number, the first Betti number is non-zero, the invariant is zero. So what you get, TQFT would have just zero-dimensional vector spaces. But we can overcome this abstraction. It's relatively recently. We can solve this abstraction, but at the price we pay that some three cobordisms are forced to be decorated by ribbon graphs that leads to one edge colored by projective object of C. So when C is not semi-simple, projective objects play a central role. The idea is that the subcategory of projective objects, it admits its own trace. It's a non-degenerate trace from the ideal, which replaces the usual categorical trace. Because when C is not semi-simple, usual categorical trace on endomorphism of projective objects is zero. So there are two key points: non-trivial trace on ideal projective objects and modified cobordist category. But it's still an interesting construction. So let me give you more precise what I mean by this cobordist category. So the objects are standard objects in standard cobordist category. They are surfaces. Surfaces might have punctures, they might have no punctures. And the punctures of my surface, they're labeled by objects of my category. So this is my input data, right? And then I have equivalences classes. My morphisms are equivalences classes of such pairs. So between surface sigma and sigma prime, and M is a three-dimensional cobordism. And if I have non-trivial punctures colored by objects, inside this M I have a ribbon graph propagated. Steve. Okay. And then there is this admissibility condition. We formally say that, okay, every connected component of M disjoint from incoming surface should contain a subgraph of T with at least one edge labeled by projective object. So if C is semi-simple, then this admissibility condition is empty. In semi-simple case, because tensor unit is projected and it changes nothing. So it's only when C is not semi-simple, it's very much trivial condition. And these cobordism categories, for check, they are not rigid compared to usual cobordism categories. So we have no coevaluation for surfaces, for example, with no punctures. So it's missing, this category is missing some coordinates. So only, for example, only surfaces with a puncture followed by projected objects, they have tools. But otherwise, Cope C contains many interesting coordinates still. For example, standard non-decorated mapping cylinders, they're all there. So it's just some coevaluation maps, just that's it. But at least with this category, we can construct a TQFT. So this is theorem of paper we wrote with Marco Dorenzi, Nathan Gear, Patirolo Milan, and Ingo Runkel in 2019. It's a base, of course, of many previous works, in particular, based on ideas of the paper of Blanchek, Constantino Gear, Patirolo in 2014, and Dorenzi and Gear, Patirolo in 2018. So what we provide, if you give me any model tensor category of an algebraic closed field, I can construct you a symmetric monoidal function from this cobordism category I have defined to finite dimensional vector spaces, such that it evaluates every surface of genus G to this vector space is just forming my category of G tensor power of L into 1. More generally, if I have punctures and punctures are colored, it will become space of tensor product of colors of the functions tensor LG, tensor 1. So let me give you some examples. So these TQFT state spaces, they're quite natural. So a surface sphere is evaluated to the ground field. Torus is evaluated to the morphism of identity functor, or sort of center of algebraic center of your category. So it's end transformation of identity functor. Surface of genus 2 is evaluated to endomorphisms of this L as an object in the category, which is the same as end transformations of a functor tensoring to objects. So tensoring to objects, the functor from C plus C to C, right? And you take, the whole algebra of end transformation to such functor. And in general, surface of genus G is related to end transformations of the functor taking G objects and smashing them into one, tensering them all. So it's very natural functors. So actually, manual structure or in the transformation of these multiple tensor functors, tensor product functors, they are my TQFT state space. Okay, so quite natural. Also, 1 year later, we proved that this TQFT, because it contains all mapping cylinders, you can ask what mapping representation it generates. We proved that this mapping class representation, they are this TQFT generates, they are projectively equivalent to those I mentioned introduced by Lubashenko on the formal level in 1994. So they generate something that was known, but now we have a TQFT construction. Such known. And in many examples, we prove, in a few examples, we prove, still in the family of examples, basically small quantum set 2, model tensor categories, or model tensor categories for symplectic fermions, that if you take surface genus G and any simple closed curve, the density action corresponding to that closed curve evaluated under this TQFT has infinite order. So every density has infinite order. This is the representations we get. That's why this construction is infinite, because we get completely different mathematical representations compared to the previous construction of Drive. So that's what I mentioned, that this infinite order of densities never happens for semi-simple MTCs, and therefore topological information carried by this TQFT is not contained in the one carried by TQFT of Drive associated to semi-simplification of the category. Let me give you an example. of these mapping class representations, again, for symplectic fermions, for my favorite model tensor category, this we studied in the paper also with Ingo and our previous student Farsad. In this example, the torus, the vector space corresponding to torus has dimension 3 plus 2 to the n minus 1. And projective SL2Z action is, it has this decomposition. There is a 3-dimensional direct summons. And there is a bunch of tensor products of fundamental representations of SL2Z. And okay, but this 3-dimensional guy is coming kind of from characters of projective objects in a sense. And in some cases it's reducible, in some cases it's split, but it always has the T action diagonalizing. So on this guy, all dentries they act by finite order. But infinite order of dentries is responsible for the appearance of this fundamental representation of SL2Z, because T matrix has a Jordan block. That's why we have infinite order representations. And this mapping class group is responsible for this invariance of length spaces I mentioned before. Okay, so what about the manifold invariance? Because associated with these two theories. First of all, because of this condition of cobordisms I have, in particular, closed cobordisms, so from empty to empty, or closed manifolds, they have to have inside a non-trivial ribbon graph with at least one edge covered by projective object. For example, it can be, so this is the picture for what is allowed in manifolds category. Again, it can be length space, so I have the surgery link, but inside I at least have to have, for example, a loop colored by projective cover of tensor U, for example. It might just live in 3-ball. So the 3-ball graph doesn't need to see lots of topology, it just needs to be live in 3-ball. Or the situation might be more interesting, where your loop or ribbon graph is entwined, so it goes along a non-trivial homology side of your manifold. So this is typical situation we are going to consider for manifolds. And actually, in this type of situation, because this guy lives in a 3-ball, it doesn't affect much of topology. So one can show that the manifold invariant for this, like length space with such embedded ribbon graph is just proportional to the Lubashenko invariant. So in some sense, Lubashenko invariants are contained. This TQFT also provides by this trick Lubashenko invariants. But there are much more interesting cases where ribbon graphs is entwined with a link. And okay, I will give you some examples of this, and I will explain why it's interesting. But from this perspective, if we forget about TQFT now, just thinking about three-manifold invariants, we can actually define three-manifold invariants with these ribbon graphs, again, same condition. But the objects, they don't need to be necessarily from projective ideal. They don't need to be projective objects. They can be objects from any tensor ideal. So I'm going to give you, so the idea that choosing tensor ideal in my non-semisimple model tensor category, and if it admits a trace, I will talk about it now, then I give you a series of invariants. So for different tensor ideals, we get different series of invariants. Okay, let me spend some time talking about tensor ideals. Pavel mentioned ideals, but my ideals are different. They're sometimes called thick tensor ideals, because it's a full subcategory in my category, such that for all x in my ideal in this subcategory, and any b in my category, tensoring on right is again in my full subcategory. So it's like for right ideals of boundaries. And it should be closed under its properties. And in our abelian case and identity category case, that means that direct summons of object in ideal, they are also in ideal. And let me give you trivial examples. Ideal with zero object or ideal in book category. The next important example is projective ideal or ideal of projective objects. Why it's an ideal? It's just because we have rigidity. So, I mean, to see that each projective object form an ideal, let's tensor it with any object P, and let's look at this functor, and let's show that it's exact. But because of rigidity, I can prove V on the other side. So this functor is isomorphic functor P, argument tensor V star. And I didn't mention, but async rigidity forces this category to have a tensor product which is exact. So tensor product is exact in both arguments, left and right. So this function is just composition of exact functions because the first we are tensoring, it's exact, and then P is projected. So home from P to anything is also exact. So this shows that P tensor V is projected, right? So that's why it's ideal. And for me, the very big source of ideals, we call pullback ideals. So assume I have now a tensor functor between C and D, and let G be of I be a right ideal of target of my function. For example, this right ideal might be proj of D. And then we can look at the subcategory of pullback along this functor of ideal I. So it's a full subcategory consisting of objects now in the source of the functor such that they all map to that ideal. And because functor is a tensor or a strong one of the functor, because of this, such a pullback subcategory of pullbacks is a tensor ideal in C. And this way, playing with these functors and the target ideal, you can always choose, for example, projective G, project objects. Playing with different functors, you can construct many interesting ideals in your category. And for me, in Hopf algebra case, it's very simple. For example, you have a Hopf algebra, you have B, Hopf subalgebra in H, and take F a restriction functor to Hopf subalgebra, it's a monomial functor. And then this restriction star pullback of tensor ideal projective B modules, it's just the right tensor ideal in H mod of those H modules that are projective over B. Okay, so now some properties of tensor ideals. So projective ideal projective object, first of all, is generated by any non-zero projective object. And it's the most fundamental ideal. It contains no right or left subideals other than zero itself. So proper simple ideal. And if G is a non-zero right or left ideal in C, then proj C is subideal of G. So proj is contained in any ideal, in every ideal of the category. And the category admits a non-zero ideal, tensor ideal, if and only if it's semi-simple, even only if it's not semi-simple. So if category is semi-simple, there are no ideals, except 0 and C. Okay, now assume a category is not semi-simple, and assume I is a proper tensor ideal in my tensor category. Here I use also conditions about equivality. Then categorical trace on every tensor ideal is 0. Okay, that's why standard statistical derived construction will not see a difference between non-semi-simple category and its semi-simplification, because it's 0 on every ideal. So we have, one can also show that we have inclusions. So we have this fundamental ideal projective objects. Then we have category C. It contains a proper ideal of annihilator of this categorical trace. Right, basically all objects, only negligible objects, or all objects with 0 quantum dimension or with 0 categorical dimension. And between them, and this is kind of biggest ideal, biggest proper ideal. It contains every other ideal. But in between, there is lots of interesting stuff happening. Typically, you have continuum of distinguished tensor ideals, and these intermediate guys I call intermediate tensor ideals, and they will play an important role. Let me give you an example of such intermediate ideals. ideal between approach C and annihilator of categorical trace. These are pullback ideals. So, for example, in the case of our exterior algebra and even dimensional vector space, just take any proper subspace of this of my 2n dimensional vector space, and it defines you a tensor ideal using restriction pointer to exterior algebra of that subspace, right? So exterior algebra of this subspace is the Hopf subalgebra. In my big Hopf algebra, total exterior, and so by this previous construction, taking pullback and restriction functor, you get an ideal. And they will be all different. I mean, they will all look alike if P has same dimension, but still they are all different. So you can see that we have continuously many tensor ideals. And you can change dimension of B, you get some network structure of ideals. And for my topological examples, I will use the case n equal 2. And I will, in 4-dimensional vector space, I will consider 2-dimensional vector space. And the corresponding tensor ideal of this 2-dimensional vector space, if you want again, it's modules of an exterior algebra of 4-dimensional vector space, such that under restriction they project over exterior algebra of 2-dimensional vector space. And this ideal has a continuum of isoclasses of 4-dimensional decomposables. So it's called P mu. So projective ideal has only 2 objects. But this pullback ideal has already continuum. They have dimension 4. They parameterize by matrices 2 times 2. So there are 4 parameters, 4 complex parameters, and I repackage them into matrix 2 times 2. And these P mu guys, they correspond to all possible leaves of projective cover of tensor union for 2-dimensional vector space, leads to module structure for 4-dimensional exterior algebra of 4-dimensional vector space. And these parameters mu, they basically correspond to extensions. So they correspond to extensions between simple objects, but with respect to big algebra. Okay. Now I need to talk about traces because we need traces. So the idea is that we are going to label our graphs or links in 3 manifolds by object in the ideals. But to calculate invariant, we need a trace. And as you know, I just say the categorical trace will not do the job because categorical trace is 0 in the endomorphism of any object of any tensor ideal. So, and it was a long story starting from work with Gil, Pativan, 2009, and then was developed further with Belizier and Java. They came with the idea of trace on tensor ideals. And at that time, it's also known as a modified trace. But I just prefer to call trace on tensor ideals. So it's a higher linear maps. It's fine 2 axioms. First of all, it should be cyclic, as usual trace. It's a linear cyclic condition, but it should be also compatible with duality structure. So because P is in my ideal, X is any object in C, P tensor X is also in ideal, so we can evaluate P tensor X on any endomorphism of P tensor X. And it should be equal when you do a partial trace. So we just take a partial categorical trace. What we want, we close this second strand using evaluation to evaluation maps, but keep strand P, and it should be TP. Right. So this is a partial trace condition. And let me give you examples. So of traces, if C is semi-simple, then project C is a full C, and modified trace is just categorical trace, and it's unique up to scalar. If C is non-semi-simple, then project C is subcategory. It's a proper subideal in C. As we know, categorical trace is 0, but you can show if modified trace of project C exists, it's non-degenerate. So it's quite opposite to categorical trace. So the question is when it exists. It not always exists. And so okay, the first idea, I think the first result on these traces and projective ideals was by Gil, Java, and Turo in 2013. In the case, if you have a simple projective object. So the idea is simple. if you have a simple projective object, then any endomorphism of projective object is described by a scalar, right? And why categorical trace is 0? Because when you calculate categorical trace, it is this scalar times dimension of projective object. Its type here should be P. And it's 0 because dimension is 0. But why not to keep a scalar itself instead and try to extend? So and hold the and take this scalar as the value of a new trace on projective object. And try to extend it to the full ideal, and this is what they did. So the indeed exists if the category is pivotal and unimodular. Unimodular means that tends to cover certain self-duality condition on projective cover of the unit. And then with my paper with Ingo in 2017, we showed that if C is in particular modular as a category, we prove that if it's modular, then it has a simple projective object. It's necessarily has a simple projective. And then by the theorem, it has a modified trace. And then later, but again, so these are recent results of modified traces. But we need to compute them. And a way to compute them is very easy to demonstrate in the Hopf algebra case. Back in 2018, with Belyakov and Blanchet, we proved this theorem, which explicitly gives you explicit formula of such a trace on the projective idea. So I assume my Hopf algebra is unimodular and pivotal. And then we proved that the space of right modified traces from projective ideal of H mod is the space of, symmetrized, you can ignore it for the moment. It's a space of just right integrals on H. And so it's one-dimensional. And the formula for the modified trace or the trace of projective ideal is given by, it's uniquely determined by this formula. So you start with endomorphism, any H linear map of your projective generator H. H is a projective object, but it's even a projective generator. And the value of the trace is just, you have to evaluate this endomorphism on the unit, you get element in algebra, and you have to evaluate integral of the Hopf algebra, and mu G is integral shifted by pivotal element. And you have to just evaluate image of one under this section. Right, and this is very useful because in examples we are studying, typically it's very hard to, from general principles to find the traces, but the integrals we know. The integral is not hard to calculate, or at least for example, for algebras and considered. So before that, we can relate traces to integrals. Okay, let's skip this, and later also with my previous student Montalvo Orozco, we also constructed such traces on ideals, on pullback ideals. For example, in a Hopf algebra case, if you have a Hopf subalgebra in a Hopf algebra H, which shares the same pivotal element, we have a trace on the tensor ideal of H modules which are projected over this Hopf subalgebra, and this trace is uniquely determined by the right integral of that Hopf subalgebra. Okay, and we have explicit formula, and this is our main computational tool for topological invariants. So, what do you do with topological invariants? Okay, so if you have a Riemann graph followed by object in my ideal, say P is in my ideal, I have a framed link. Just take one component of that link or edge of your graph, cut it, and pull the strands up and down. So this is what you get in the box TP. It's a cutting presentation of your Riemann graph or link. And then you should interpret such one rectangle as a morphism in the category. You just use all structural maps to write such a morphism. And you just evaluate modified trace or trace on such a morphism, where P is in my ideal. And this is well defined invariant, isotropic invariant of your Riemann graph or your link. The non-trivial fact is that it does not depend how you cut and which edge or which link component you take, because several might be labeled by different objects for the same idea. Okay. So the idea is that we use this, in the same paper I mentioned when we defined the TPFT, non-semisimple TPFTs, we actually gave a definition of closed connected free manifolds with a ribbon graph such that at least one edge is colored by object from my tensor ideal. Or if you want, in simple situation, you have a ribbon graph, you have free manifold, and you have a node colored by object in that tensor ideal. And for such a thing, such a node inside a free manifold, we can give you, we can explicitly calculate free manifold. I don't have time to, there is a construction. It involves, it's kind of combination of Lubashenko invariant, Lubashenko construction, using surgery, and the trace on ideals. Okay, so I will skip this. Right. I think I will go to my last slide. Right. About examples. Okay. So let's go back to length spaces. And so, as I mentioned, is that theorem that for you choose it's your input data, category C, model tensor category C, and the choice of tensor ideal with a trace on it. And for every such a choice, you get a series of invariants. And let's see how these invariants depend on the choice of my ideals in my category of symplectic fermions. So this is very basic non-semisimple category of four-dimensional stereo algebra, four-dimensional vector space. Here, alpha is a natural and the transformation. I mean, this box is just for a node. It can be not, but let's do it for alpha identity. So nothing, just loop going around this last surgery component. And by the way, here I have a description that because of course the surgery is not uniquely defined, but here I have a prescription that so this for length space PQ. So AN is I take sailing of P over Q, and AN minus 1 is inverse of P over Q minus 1, and so on. So here I have some description of how I do what sort of representation I take. So if I give the whole category C, I forgot to mention maybe in this result with this paper with Johannes Berger, we proved that for these three manifold invariants, if your choice of ideal is the whole category C and T is the framed link in that manifold, then this invariant depends only on the Grothendieck class of objects labeling T. So, and in this case, we get a Lubashenko manifold invariant. So if your ideal is the whole category C, you don't need to label it by complicated objects. It's not labeled by simple objects, because the result anyway depends on the class label. And in this case, you don't have much choice. You can label by tensor unit, for example. And in this case, you get this Lubashenko invariant, which will be so. It was a power of order of fourth homology group. In this case, it's just P squared. Invariant of LPQ is P squared. If you take projective ideal, and we can label the loop by projective power of tensor unit. So it's big guy, dimension 16, and the invariant of this pair length space with this non-trivial loop is a Q squared. But you can do actually better. And what is interesting is to look at intermediate ideals, these pullback ideals I will describe. And now, remember for this situation with two-dimensional vector space in four-dimensional vector space, I have this pullback ideal which contains continuously many non-equivalent indecomposable objects, P mu. They're labeled by this matrix, matrix 2 times 2. It has dimension 4, and they all have same composition series. So they have all same composition series, but there are these extensions parameterized by mu. And the invariant, my invariant of the length space now with this loop, but labeled by color by this P mu. What is interesting is it distinguishes all P and Q, it's 2PQ, and 1 plus determinant of mu of this matrix mu. So what we see that this tensor ideal, bigger tensor, intermediate ideal, it I mean, with different ideas, they contain different topological information. So this ideal is in some sense more interesting because it can distinguish all the spaces, but it also this invariant sees internal structure of the object labeling. So let me conclude that these non-semisimple invariants based on intermediate ideals, they are able to distinguish a continuum of decomposable but reducible objects to the same composition series. These invariants are able to detect extensions of the object labeling my link. And so the invariant that able to detect extensions I call algebraically strong invariants because they can see internal structure of object. And it happened that algebraically strong invariants also topologically strong. Okay, that's finished.
So for how you sort of imagine the use of topological variants? So how are you imagining using these topological variants? Do you want the theory of all of these intermediate ideals to get like full variant? Is there like my ideal intermediate ideal that already gives you the full would be really very
No. I'm saying okay. I'm saying that if your ideal is the whole category C, you can still label your object by any object in the ideal, right? I mean, by any object in the category C, but it will not distinguish between split and non-split extensions.
Yeah.
Right, because as I said, for whatever manifold, I mean, if you label a link inside the manifold by any object, for this use of ideal, it will only depend on the synthetic class.
Yes.
So I call it algebraically weak. Okay. Or for simplicity, you could even think about a three, like just three-dimensional sphere, and talk about invariant of links, just rings in S3. And when you choose ideal C, standard just interact for any contact, right? It gives you invariant of this link, but this invariant will not see internal structure. And then the invariant defined by these modified traces or traces from ideals, like projective ideal also doesn't see lots of internal structure because typically you don't have so many projectors. But what is interesting, if you go to intermediate ideals, like for example by this Kuba construction, they will typically contain continuously many objects. And this continuous parameter is responsible for non-trivial extensions. And the invariant, for example, a link using this trace of such an ideal, as you can see in this example, it sees some of the internal structure. Ideal is fixed, but it will distinguish objects with the same composition series in the same ideal. So that's why I call such invariant algebraically strong because it can detect extensions, and and that's why this invariant is observed to be called non-semisimple. It's not just the input of the category non-semisimple; is that invariant can kind of see internal structure of objects in your category.
Yeah, I understood that you see all of the internal structure, all of the
Oh, yeah, okay. Yeah. Of course, I will not see all objects because I mean, I can detect. No, but okay, if you fix an ideal, here I don't see all the determinants of but for example, if I take some non-trivial node, it will see other, because it will be another function of these four parameters.
No more questions. If not, then that's very much.